So as we saw in the previous video, there's plenty of situations in which we have a certain third variable that is causing us trouble. It might look like we could in principle say that one independent variable is causing the change in a dependent variable, but it's actually because of another variable that we are not aware of, and it's actually fooling us. Let me show you another example here. In this plot, we have the relationship between the CO2 levels in the planet and the temperature in the planet, going back hundreds of thousands of years. This comes from a documentary from Al Gore. And what we could see here is that there's a very clear relationship, right? When the temperature goes up, CO2 goes up, or maybe the other way around. It actually is the case that sometimes the increase in temperature goes before the increase in CO2, and some other times that it's the other way around. But in any case, what Al Gore was saying in his famous documentary was that the two graphs obviously move in lockstep with each other. And when there's more carbon dioxide, the temperature just gets warmer. So essentially what we were saying is more CO2 causes more temperature. Now, first of all, we know from the previous video that when we have two numerical variables, the best way to plot the data is usually scatter plot. So let's take a look. If we show a scatter plot of CO2 and temperature, what we have is this very clear, positive, kind of linear and strong relationship. So there's this very clear correlation between the CO2 level and the temperature. And the thing is, it's not just one straight line, right? There's a certain amount of variation. And that could be because, well, first of all, the precision or the reliability in how we measure the different levels of CO2 and temperature. But most likely it is because there is something else beyond CO2 that is also causing the temperature to rise. And if we look at the data from today, or actually today years ago, when these data were presented, we see that there's something funny, right? Over here, the temperature nowadays is a lot higher than it should, according to the rest of the data. And so much that if we were actually to plot it, we see that today is over here. There is a very huge difference between what we are measuring today and what we should have been according to the rest of the data. And we know that, yeah, it's not only CO2. There's more gases, more greenhouse effect gases like methane that are causing the temperature to rise. And we know that the causality is actually not that clear because sometimes the CO2 rises with temperature, some other times it's the other way around. It has to do with evaporation of water in the oceans and more raining, etc., etc. There's plenty of other things that influence this process of the planet getting warmer. It's not just CO2. And so I'm, of course, not denying global warming. What I'm saying is, if we just look at this data, it's telling us there is something else. So we can't just say more CO2 equals more temperature. Well, yes, and other times it's the other way around, and it's not only CO2. There's other factors that we have to take into account. Another very clear example is the number of storks and birth rate. You know the story. Apparently, the babies are delivered through storks that travel all the way from Paris to whatever they have to deliver the baby. And if you look at data, each of these observations corresponds to one place, and we see that there is a very clear correlation between the number of storks and the birth rate. So in principle, where there are more storks, there are more babies. So we could say the story is true, right? But actually it's because of something else. It just happens that in large places, there are more storks, and in large places, there are also more people and therefore more babies. So it's actually this third variable that is making the change in both the birth rate and the number of storks. And it's just the area of the place. So how big the place is. And we can look here at a very clear positive correlation between the number of storks and the area, a very clear positive correlation between the number of babies and the area. So there's this third variable that would have fooled us if we just look at the previous plot and say there is causality between storks and babies. And so in principle, we like to think about these third variables in two categories, either lurking variables or confounding variables. The lurking variables are those that are unknown to us. We have no idea about them. And they are actually the ones causing the variation in both the dependent variable and the independent variable too. And this is usually a result of poor planning in the research studies. And when we're planning what concepts to measure and how to measure them, we're just missing this one factor that is crucial to the relationship we're looking for. The example I like to give is the one about firefighters and the damage from the fire. So let's say we have the data from the city hall, and we have on the one column the damage from the fire, we have the data, and on the other hand, we have the number of firefighters and the data. Those two are, of course, going to be correlated, right? The higher the damage, the higher the number of firefighters, usually, because we just send more people whenever there's expected to be more damage. So if we just look at the two columns of data, one might be inclined to say, look, stop sending firefighters to the fires because they're causing more damage. And that's, of course, ridiculous, right? That's completely nuts. But it could be something that one might say just by looking at the very clear positive correlation. And it's actually because of a third variable that we are missing here, which is the size of the fire. If we had that column of data, we would see that it's actually the size that is causing more damage, of course, and more firefighters. So the number of firefighters and the damage of the fire, it's actually caused by the size. If we were to ignore it, if we just had the data set with these two columns of data, we would be inclined sometimes to make completely stupid claims like that one. And it's just because of a lurking variable, in this case the size, that we are just ignoring. The other kind of variables is confounding variables. And those are things that are actually known to us. We have them in the data set. We could be able to measure them. But they cause the variation in the dependent variable, and the things that they affect cannot be distinguished from that of other independent variables. So it could be the case in which we do have the variable, we have the column of numbers, but we are not certain whether the variation in the response is caused by this variable or another one. We cannot tell apart the effect of one from the effect of the other. And it's usually a result of a poor design. So even if we know that we have to measure that one variable, there's no way for us to tell apart one from the other because of a poor design. We'll talk about it in a few videos. And think about the case in which we are trying to figure out what's the effect of different coffee brands, let's say 2 different coffee brands, on the aroma or the quality of coffee. But the point is, we're always going to brew one brand of coffee with one machine and the other brand of coffee with another machine. And then if we do that, and we observe a difference between the 2 brands of coffee, then there's no way for us to know whether that difference is because of the machine or because of the coffee brand. There's no way, regardless of how much data we have and regardless of what kind of statistics we apply, there's no way for us to tell the difference between one or the other, because in this case, the brand of coffee and the machine are confounded with each other. We cannot tell apart the effect of one or the other on the response. Again, we will see more about this in a few videos. And so the thing with the third variables is, for instance, time or the area that we saw earlier for the storks, it's often a problematic third variable because things just happen to evolve with time. It's just their natural process. And that's why we're going to find plenty of spurious correlations because of the effect of time or other group properties such as the size. Think about the birth rate and number of buildings. If we were to plot data, we see that we have over the years more and more buildings, and we also have more and more babies. That doesn't mean that buildings are causing babies. They just happen to be correlated because of the natural evolution through time. Or CO2 emissions and obesity. We know that we humans are getting more and more obese with time, and there's more CO2. That doesn't mean that one is causing the other. It's us, more people, that is causing those two. Storks and babies, like we saw earlier, or COVID-19 deaths by country. Larger countries with more people, higher population, they are going to have more casualties. Well, because there's more people to begin with. It doesn't make sense to compare absolute numbers across countries. We should always compare percentages, right? So it could be that we have an improper analysis that hides or even reverses these fundamental relationships. Things like we miss an effect, we miss an interaction between multiple factors, the data are imbalanced, and we maybe have nonlinear relationships, we don't have statistical power. There's plenty of reasons why we could miss these relationships. We will talk about them throughout the course. But basically, maybe just the independent variables are not the main or sole reason or the main or sole cause for a certain effect in a response, especially if we're modeling complex phenomena, because usually there's a multitude of variables that are involved in a certain process that ultimately leads to a change in an outcome. And if humans are involved, even more so, because we can't model human behavior. It's next to impossible. Another example, COVID-19 testing policies. So we might see where or in which countries we have more positives. Well, everything depends on the testing policies. Who are the people being tested? Do they test when they show symptoms? Do they test multiple times? Do they only test if they go to a hospital? Do they test especially elderly? Do they test children? Every country has a very different testing policy. So in the end, we cannot really look at the numbers from one country and the other because those are essentially apples and oranges. There's plenty of reasons why a country might have a higher positive rate. That could be they're testing more. They're testing more to people who are presupposed to have the virus, not others that are just testing preventively. There's plenty of reasons why we could see one difference between countries. And another way of categorizing the third variables could be mediating or moderating. So mediating variables are those that are linking the independent and the dependent variable or somehow facilitate the relationship. So it's the one that is responsible for the link between the two. Think about better driving. That could be an outcome, a variable, a dependent variable, and how it correlates with the age. We know that the older we get, the better we drive. But it's not because we are older, it's because we getting older means we are more cautious. And so we are going to drive better because we're more careful. It's not a direct consequence of being older, it's because being older means normally that we are more cautious and therefore we drive better. But also if we continue getting older, our reflexes go down, and so our driving starts to go down as well. And in this case, both being cautious and having or not reflexes are the mediating variables that facilitate the relationship between the quality of driving and the age. And then we have moderating variables that are those that influence the relationship between the independent variable and the dependent variable. So think about the relationship between the social class and the frequency with which women self-examine for breast cancer. We see that people of higher social classes, they tend to self-examine more often, but once they get a certain age, there's no difference between them. So older women in all different social classes, they tend to have the same frequency of self-examination. So there is this relationship between the social class and the frequency of self-examination, but it's moderated by the age of the person. And so this relationship depends on this third variable, that is the age. And so when we have this comprehensive study we were talking about, where we make the distinction between factors we can control and factors we cannot control, we also think about factors that we don't know about, so unknown factors, things that we just don't know that are there, and they are actually playing a role in the process, and they might be even fundamental. And so it's not so much about what is the effect of the factors on the response. What's important to ask is what is the effect of those factors of interest on the response while controlling for the other effects. So if I'm interested in something specific here and the effect on the response, it's important that we control for all these other things so that we moderate, mediate, etc. Let's see more examples. So in this oversimplified study in which we wanted to look at the door-to-door time of people traveling home from work, we were just interested in the effect of the different transportation mode. But if we think about it, there's plenty of other things that could affect the response, right? So for example, it could be the ticket price. It could be uncontrollable factors such as the congestion of the roads, the weather, Maybe if it's raining, people don't take the bike. Maybe they just prefer to go to the bus. Unknown factors. Maybe I don't take the bike because my physical condition is not so good. Or maybe the mechanical wear out of the trains, and then we start having failures and it takes longer. If we could control for those things, we could have a more suitable answer to the question of what is the effect of the transportation mode on the door-to-door time. We have to control for those things. Another example we saw was the surgical procedure to operate on a certain patient, and then looking at the recovery time. Again, there's plenty of other factors that influence the recovery time. We could think, for instance, about the equipment, might be something that we can control. So maybe there's a surgical procedure that works very well only if we use a certain kind of equipment. We need to control for that variable. And then there's plenty of other factors that we can measure, but we cannot control. Say, maybe the surgeon. We cannot decide who's going to operate. We, of course, cannot decide on the age of the patient or the severity of the sickness they have. And then we have unknown factors, things that we don't know about and might be related to this, such as other medical conditions. Maybe they have another condition that is making a change or is making them recover later or sooner. In the end, again, it's about testing what is the effect of the surgical procedure on the recovery time while controlling for all these other factors that surely affect the process.